the dark bits of the painting, the parts of the painting that should be red and are turning black are mercury chloride in the region where it was cleaned. And that was because it was cleaned with an agent that contained chlorine, and we now know is harmful to this process. So one of the things that we're doing, I should say instead, this is not actually work done at Diamond. One of the things that we are doing is using very similar techniques to inform people curating pictures about restoration processes and what is harmful and not. Another piece of work, and some of you may have seen this kind of work. This is a lovely piece of work from museums, mostly in the Netherlands, and it illustrates the use of X-rays to look underneath a painting. So Van Gogh, for example, for most of his life was very poor, and he had to reuse his materials. He would often take an old painting of his and paint over it, and reuse it, and produce a more modern composition. So underneath the top left picture is just called Field of Grass. You can perform X-ray radiography measurements with simple portable devices, just doing a radiography, the absorption of X-rays, and what this reveals is a rather faint image, if you look at the bottom left, of a woman's head. Now, that's just looking at the difference of absorption of X-rays, because the paint that he used contained different elements: mercury, antimony, zinc, and these have different X-ray absorbances. The cleverer thing, however, is to determine exactly what elements there are in the image underneath the top coat of paint. And what people at ESRF did, and at the Daisy synchrotron in Hamburg, was to selectively look at the emission of X-rays for different elements when the picture was irradiated with X-rays. So if you apply a filter and you say, where is the lead? You see this image here. The lead has no image of a face, it's uniformly spread. That's because the lead that's present in this was just a primer coat. It was an even coat of lead oxide. However, if you set the filter for antimony, which is the basis of yellow and white pigments, you start to see the image of a face, because the yellow, some of the tones of the skin involved yellow or white. And if you carry on that process, you can show, now I'm blind, so I don't see this very clearly, but you can see that the mercury is found on the lips, not surprising, because mercury is the common base of red pigments, and there is also zinc, and we see zinc, which is a white, usually used in a white pigment, around the eyes. So one question is, what form does the antimony take? And you can use very precise synchrotron X-ray measurements to say, not only is the element antimony, which has, the chemical symbol for that is Sb, not only is there antimony distributed like in the top right figure, but you can even look in greater detail at what form of antimony is present. And what the measurements deduced, without having to expose the picture, is the antimony is a yellow form and not a white form. And you can put all this information together and you can reconstruct. So you can look at all the possible elements, you can determine to some precision what form those elements, what chemical compound those elements are, and then you can simulate, if you like. You can say, well, the antimony is a yellow form of antimony, and you've got red on the lips, and you've got white in the eyes, and you can generate the image of the face hidden under the canvas. And what's nice in this case is there's a striking resemblance of this woman's face to sketches, or rather paintings that Van Gogh did a few years earlier that have been preserved, that have not been painted over, which he used as a series of studies for exercises in light and form, using as model a particular peasant woman in the Netherlands. And just to finish this, to say that this, of course, is done completely non-destructively. The painting is put in the beam, it wasn't damaged. Parts of the painting were already damaged, there were flakes of paint, and when the paint was removed, they could be studied again with X-rays, and in the right-hand side you see a cross-section, and what you see in this picture is the top part of the picture represents the upper surface of the painting, That's your grass, the picture of the grass landscape. Then you have a thick layer of lead oxide, and underneath that's the original painting. So this is the original painting, a thick layer of white lead oxide as a primer, and then the more recent field of grass picture painted on the top. Now, the example from Diamond, I talked earlier about preservation. Probably our most prominent recent example of preservation is the work that we have done on Henry VIII's favourite battleship. So the Mary Rose was the pride of his fleet, and she sank in the Battle of the Solent, in the middle of the 16th century. And there's a picture, I think a tapestry, that records this at the time. Henry VIII can be seen somewhere in the crowd. The detail doesn't record whether he's happy or not, but anyway, the ship sank in 1545, and it lay under the water until 1982. And it was largely preserved because it was covered by mud, and the mud protected the wood of the ship from oxidation from the air. So this ship was discovered in the 1960s. It was raised to the surface, and then the process of conservation started. Now, some of you may be familiar with the Vasa project. So in Stockholm, there's this wonderful preserved boat that was raised from the bed of the estuary or river, I'm not sure which, near Stockholm, 20 years before this work was done. And they pioneered the process of the wood preservation. What you have to do is you have to replace the water by a polymer, which gives some sort of stability to the wood. You can't keep it wet because it would then be very difficult to display it to the public and be kept wet. So the first step of the preservation process is to replace the water very gradually over several decades with a polymer that displaces the water, and then the heavier form of the polymer goes into the pores and cells in the wood and actually acts as a structural support for the wood itself. Okay, so that slope, and then at that point you replaced all the water by polymer. You can take the remaining water away and you can dry it out. And they did that with the Vasa. The problem is, shortly after they started to display it to the public, the wood started to rot. And the reason was they'd forgotten, or they weren't aware of, one key element, and that is the wood was full of sulfur that had been deposited there by bacteria. And once the wood was exposed to the air, the sulfur started to oxidize into sulfates, and where the wood was in contact with iron, for example in the nails in the wood, there was a chemical reaction. Iron plus sulfate, in this case, makes sulfuric acid. And the sulfuric acid, in the case of the Vasa, was destroying the wood. So in the case of the Mary Rose, the question is, how can we protect the wood against this process? So we worked carefully with them, first of all, to develop techniques to measure where the sulfur was and in what form it was. So we were able to use spectroscopy to make maps. So the photograph here is just a regular photograph of a piece of wood. In the hole is where a nail was. And we were able to make maps showing where the sulfur is in the wood and what form it is, saying, here you have sulfur and it's sulfuric acid, or it's in the form of sulfate. A technique was developed to stabilize, to essentially to neutralize that chemical process and to stop the conversion of sulfur to acidic sulfates anymore. And then we worked with the conservation people to demonstrate that the technique was working. Because what you don't want to do is say, I've solved the problem, start to display the boat to the public in air where the public can walk around, and then discover that the rotting process, the oxidation, is still continuing. So we have a continued collaboration with these people, and every year we take a sample from the wood and we demonstrate that the sulfur, the conversion of sulfur to acidic sulfates has stopped. And over the last 3 or 4 years, because this is all very recent, it really appears that the wood has been stabilized against this corrosive process. And you can visit this wonderful ship now in a museum in Portsmouth Dockyard, in England. I think that's, oh yes, last example of spectroscopy. So one of my favorite graphic artists is J.M.W. Turner, who, among other things, painted these wonderful, almost impressionistic landscapes. Many of them in the UK, places I know. On the right, so on the left, is a classic example of Turner, and you see his very distinctive use of blue, and he used a pigment called Prussian blue. On the right-hand side, you see another landscape taken from, actually up the west coast of Scotland, Loch Fyne. Now, Loch Fyne might look like that on an average day in the winter, a bit like St. Petersburg today. But actually Turner intended this to be Loch Fyne with a blue sky and blue water. And you know that because if you look around the corner of the right-hand picture, you can see where the canvas, actually I don't know if it was canvas or paper, but where the fabric was protected from the sunlight by the frame. If you look at the top of the picture, it's the original blue. So there's a problem with Turner's paintings that the blues based on Prussian blue fade. There are other blues that he used which are based in pigments which are stable. Now, the theory is, and it's still a theory because the science, of course, of this is still being developed in general, the theory is that Turner's blues are fading primarily through exposure to sunlight. One of the possible ways of guarding against that process is to protect the painting by preserving it in an atmosphere that contains no oxygen. There are many processes driven by sunlight that degrade paper, canvas, certain dyes used in painting that are accelerated by the presence of oxygen in the air. So if you want to display the picture to the public, it can't be in the dark. So yes, you try and reduce the light levels, but there's still some light. So you also want to take away the other influences. So the strategy that was developed was to display the paintings in an environment, in a special kind of frame with glass under vacuum or under a gas that didn't contain oxygen. And early work indicated that this was a good strategy in general for preserving pictures, except that Prussian blue in the early measurements appeared to fade faster in the absence of oxygen, which was a very counterintuitive result. To cut a long story short, some of the work we've been doing at Diamond is looking at the mechanism of the fading process of Prussian blues. We've tried to accelerate that by exposing the Prussian blue to very bright light and then seeing with spectroscopy how the chemical structure changes according to whether you do it in oxygen or under other gases. And what we've demonstrated through an accelerated aging process, we simulate decades and decades of exposure to sunlight using very bright light, is actually, in the case of Prussian blue, the removal of oxygen is not a problem. So this establishes that if you want to stabilize the blues in Turner's paintings, that keeping them under an inert gas or a gas without oxygen is almost certainly okay. And the fading that was attributed to oxygen earlier is almost certainly due to an interaction with certain types of canvas or paper. So the last area of application, I said there was radiography, spectroscopy, is diffraction, is using X-rays to tell you about the crystal structure. Now, most of the cultural heritage objects we look at are not in the form of single crystals, like crystals of DNA or whatever. They're in the form of very small crystals, often in a powder. And when you do that diffraction experiment off a powder, you get, and again, I wish I could do the demonstration, so you'll have to take my word for it. Instead of seeing a simple single pattern of spots, you see the pattern of spots from all of the different little crystals superimposed upon each other. So what you see instead of a small number of spots is you see a set of rings which are characteristic of the structure of the powder. So X-ray diffraction gives you a fingerprint of the crystal structure, and you can turn that around. You can look inside complicated, unknown materials, and with a book of fingerprints, because we've measured thousands, if not hundreds of thousands of different materials, we could then match the complicated pattern from, well, I'll show you an example in a moment, to known materials. So the example is one of Egyptian cosmetics. So the Egyptians, in fact we walk past some in the Hermitage today, used a palette of colours based on natural minerals. So green was provided by malachite at the top, black was provided commonly by galena, which is lead sulfide, and white was provided by a form of lead oxide, or lead carbonate actually, which gave a very characteristic white colour when ground up. And in fact, the very same white colour was used in the Middle Ages and beyond to make the skin of upper-class ladies paler. Our Queen Elizabeth I famously used a lot of this lead oxide, which actually incidentally ruined her face, and with excessive use in many cases actually led to death, so it wasn't actually a particularly safe process. But nevertheless, this was used throughout the ages as the basis of white. And the question in the case of the Egyptians was, if you look at samples of cosmetics from archaeological digs, what was the composition? And much of this confirmed what was suspected. I should say this is not from Nefertiti, that's just an illustration of the use of cosmetics. But what was interesting is from the samples, in this case taken from the Louvre, is that the grey cosmetics were a mixture, as you might expect, of black and white, but the white was not the common mineral that was found in the region. The source of white pigment, mixed up with galena, was shown by X-ray diffraction to be unlike any natural form of lead mineral found in the region. It actually corresponds to a very, very rare form of the mineral, which is found in a completely different place on the planet. And what this pointed to was the ancient Egyptians, or actually they're not ancient Egyptians, they're Egyptians of a sort of middle period, had actually developed techniques to transform lead compounds into very specific white pigments. There's a very, actually, if you look at the chemistry that you need to do this, there was clearly a form of chemical industry that transformed the natural compound into a different substance altogether. And you might ask the question why? Why didn't they just use the white form of lead that lay around in Egypt? And if you look at complementary texts, it's quite clear that the Egyptians also ascribed therapeutic powers to lead compounds. I mean, yes, if you use them too much, they ruin the skin of your face. But at low levels, and they were often used on eye makeup, they're very good antibacterial agents. So they can be used to, they're bactericides, and they can be used to guard against bacterial infection. And probably the prominence put to that role meant there was an elaborate industry set up to try and develop a wider range of lead-based compounds which would describe different efficacies. I should say, by the way, that the galena also, people assumed it was just common or garden galena lying around the area. It turned out that the impurities in the galena are just not found in that part of the Middle East at all. And they'd clearly been imported over thousands of kilometers from other parts of probably Asia Minor. And it's a complete mystery why the Egyptians didn't use local galena and imported it. Two more examples. So I promised I would put my guide Tatiana in this photograph on the right. This is an illustration of analysis, a variety of synchronicity done on the nature of blue pigments. So blue, as I'm sure most of you know, was regarded as a rather rare pigment base, at least in the Middle Ages, but it was commonly used. It was often used in association with the gowns of particularly prominent features, the Virgin Mary here, or sometimes kings and queens. And the material of choice was lapis lazuli, which was very, very rare indeed, which is why it's particularly, I just got this off the internet weekend, this 2-meter-high urn made of what looks like a single block of lapis lazuli that's sitting here in the Hermitage, and I saw it this morning, and it's far more impressive in real life. Anyway, the point is that lapis lazuli was a very rare and precious commodity. So often when people commissioning paintings wrote out a contract, they would specify that the blue had to be lapis lazuli. The question is, how would they know it was lapis lazuli and not some other sort of cheaper alternative? So lapis is also this mineral here. At the time, it would have probably been come from what we now know as Afghanistan. But you also found in Europe a material called azurite, much cheaper. When it's ground up, it doesn't look very different. It's just it doesn't come from a source that's so noble. If you didn't know the difference, how would you tell? Well, you can tell by X-ray diffraction. And what's interesting, I won't go through all the details, when you examine flakes of paint in a variety of pictures from this, or altarpieces, paintings from this era, first of all, what you find is that very commonly azurite tends to be, the cheaper mineral azurite tends to be the base of the blue that you get as the base in say, the water or seas. Lapis lazuli is still used in what you might call important parts of the painting. So the mantle of this, I think, angel in the choir, and the mantle of the Virgin Mary in the same painting do contain lapis lazuli. But what the artist did was actually, and if you look at a cross-section of a flake of paint, was he only put the lapis lazuli as the sort of the expensive layer on the top. And when you do the chemical analysis, so when you do the X-ray diffraction, what you find is the blue at the top, thin layer of blue at the top, is your lapis lazuli, but the base is azurite. So I guess the contract, he honored the contract. The blues will be lapis lazuli, but a lot of the depth to the blue was actually provided by the cheaper azurite. It's also interesting, by the way, that lapis lazuli is not a single composition, it's a mixture of minerals. And you can tell from the mixture of minerals, in some cases, where it's actually come from, because different combinations give rise to different kinds of lapis. Oh, and I think that was my last example. I took one out. I was expecting to show you one more. So, by way of conclusion, and I'm sorry for all the words on this slide, what we are finding in synchrotrons is a strongly increasing demand. There are developments in the future, so future synchrotrons will allow us to do this faster. It will allow us to look at smaller regions. It will allow us to look with greater sensitivity at specific compounds. But the real barrier for us is not the technical one. The real barrier for us is the bridge between us, the physicists and the chemists, and those people who work with artifacts. So where there has been a collaboration, it's often arrived by accident. Sometimes it's because one of my scientists has a neighbor who's an archaeologist. It is as random as that often. So one of the things that we lack is actually a more coherent way of building those bridges and trying to, for us, to try to present what synchrotrons can do, and for people from the world of cultural heritage and preservation to come to us, to ask us to work with them. So there's a cultural barrier, but I'd like to say on our side we're very open to this. There are other challenges. Some objects are too large to move, so we have to look at ways of taking samples that are not harmful. And locally, some of the things that we would like to put in the beam are very, very precious. If you want to put a Van Gogh in the beam and it costs $100 million, then you need to have a very, very... I don't think they would actually put a $100 million Van Gogh in the beam, but anyway, we have to be sure that valuable cultural objects are stored securely against theft, but also so they're stored in an environment that doesn't allow them to degrade further. So I'll stop there. I see this as something, come back in 5 years' time. I think there's citation. I should say the right-hand bar in the graph is the citations for this year, and the year isn't over yet. I still think this will rise. And I'm very happy to take questions, and I understand that my friend Michael Popov would also like to make some closing remarks, because I should say, here in Russia, you have the facilities to do this sort of work, and I'm sure he will also make that point as well. So I'm happy to take questions if there is still time. Thank you. Oh, I need the headset so I can understand the questions.
Hello. Я могу задать вопрос по-русски, а не на своем блестящем английском. Профессор, вы упомянули, что посетили Эрмитаж сегодня. Какие экспонаты произвели на вас наибольшее впечатление? И что вы, может быть, сочли перспективным для исследования и для сотрудничества с Государственным Эрмитажем?
So that's a very good question. I must say, I had less than 1 hour in the Hermitage, so I could only get a first impression. For me, actually what was most impressive in some ways was the building itself. It's a wonderful building to display art in. I spent half of my time simply admiring the rooms and the quality of the space they provide to see art. And the way they're organized, I mean, they're organized in a way that gets the visitor. The visitor we had a plan this morning, we were going to go to Rembrandt and 1 or 2 other things, but the organization of the Hermitage is such that you are introduced to other art along the way that you perhaps hadn't thought of, so it's a tremendous education experience. I think in terms of analysis, that's again, it's probably not up to me to propose that, because I'm not the cultural curator, but one of the things that was noticeable in some of the collections is there are quite a lot of paintings that, at least to me, appear to be very dark, where I imagine the varnish is in need of restoration. There is, of course, I imagine, a whole debate about whether you restore paintings like this, whether you leave them their original form, or whether you try and recover some of the original colour and lighten the varnish. But if you believe in trying to go back to the original state, then I imagine there's quite a lot of other interesting work that can be done on the preservation. But is it still working? Yes. My point is, I'm very interested to hear from you, the audience, about where you see the potential. What are the most interesting problems that you think you can bring to me? Thank you.
Okay, can I ask you a question? Я буду говорить по-русски, вы просили, насколько я понял. Значит, я хотел спросить, можно получать рентгеновское излучение достаточно мощное другим способом, торможением релятивистских электронных пучков в мишенях? Вы бы не могли сказать, примерно сравнить мощность излучения синхротронного, про которое вы говорили, с мощностью вот этого излучения, какой из них мощнее, и имеет ли перспективу такой метод получения мощного рентгеновского излучения?
So I'm sorry, I couldn't actually hear because the question was too loud compared to my earpiece. Could someone tell me? Oh, it's not working. I need someone to translate. I can't hear in this earpiece very well. Okay. Could you repeat the question, please, and we'll get the interpreter to speak directly. Thank you. I'm sorry.
Я хотел спросить вас, вы используете для своих исследований мощное синхротронное излучение рентгеновское, которое получается в ускорителе. Такое, наверное, рентгеновское излучение примерно такого же диапазона мощности можно получать торможением релятивистских электронных пучков в мишенях. Вы бы не могли сравнить эти два метода и сказать, какой из них позволяет получить более мощное рентгеновское излучение?
So I have to confess, I'm not so familiar with the second type of method that you describe, but my understanding as a very non-expert in the use of electron bombardment targets is that the resolution in energy of the measurements is not as precise as the resolution you get the synchrotron measurements. So for example, in the spectroscopy, it would not be possible to distinguish between elements in different chemical environments. But I must admit, I'm far from being an expert in this.
Okay, thank you.
Thank you. Spasibo.
Firstly, I would like to say thanks for a very interesting, wide and clear presentation. And question is do you have a special station for investigation of historical heritage in the diamond synchrotron?
So this is a very good question. The answer is no, we don't, because most of the measurements I have described use the same principles that we use to look at the structure of materials for chemistry, for physics, and so forth. So at the end of the day, we're measuring structure, we're doing spectroscopy, we're doing radiography, and that means that actually we would use the same beamline to measure the structure of a powder for cultural heritage as we would use in battery research. So because the fundamental properties you're trying to measure are essentially the same, we believe that our beamline should be general purpose. However, I think you do have to do something special. You need to have dedicated staff. You need to have people who actually understand how to make the bridge between the two communities. So I employ physicists who also have a background in cultural heritage that helps the exchange. The other thing I mentioned, you need to have local facilities that enable you to store these objects safely and securely. But I think when it comes to the beamlines, I would like to think that cultural heritage can be stored, can be measured or investigated on almost any beamline in my facility. And I have 33 beamlines. Why not use 25 of them in different ways to explore cultural heritage? Thank you. Thank you. Just a moment, I need to...
Tell me please, does the neutron scattering can give additional information that you get for the samples that you irradiate in the central lab?
Very good question. Yes, is the answer. So you probably know that neutrons can penetrate materials such as lead, other heavy elements, very effectively, whereas X-rays are blocked. So if you want to look inside objects that are made of these very dense materials, actually you would use neutrons. So neutrons don't have this same fine resolution as X-rays, but there are circumstances where they provide a way of looking inside objects that you cannot. The other thing that's interesting with neutrons is that neutrons are very sensitive to light elements. So you can also look at, you can particularly look at materials that are rich in light elements like oxygen and hydrogen, which are buried inside very dense objects. And I think also the third area is metallurgy. Looking into, well, it's almost the first point again, but there's a lot of work looking at the fabrication of metal objects, the internal structure of dense metal objects with neutrons. So I could have given a complementary talk with neutrons. So I think the two are absolutely complementary. Yeah, good question. Thank you.
В музеях очень много занимаются условиями сохранности, и в частности климатологией. И у нас для сохранности экспонатов определены очень жесткие нормы по освещенности для живописи, тканей и так далее. Сегодня появились новые источники света в музее, в частности светодиодное освещение. Скажите, пожалуйста, вот ваши исследования каким-то образом могут скорректировать нормы на освещение, которые сейчас довольно жесткие? Спасибо. И вот я знаю, что в Лувре был такой пример, когда освещали Джаконду специальным светодиодным источником, который пытался компенсировать утраченные краски на полотне. Спасибо.
Yes, that's also a very interesting question. I mean, the challenge in looking at the long-term damage of light or other influences is that traditionally you needed to have a long time to study. You know, if your light is damaging it, sometimes you only discover this 10, 20, 30 years later. So one of the recent trends in this area, I don't know why I'm putting this to my ear because I'm listening to myself. One of the trends in this area is to like this. Okay, thank you. Okay. Thank you. I feel like Dr. Spock in Star Trek now. Sorry, the light. So, one of the strategies that people are adopting now is to try to accelerate the process, to study the process of aging or damage under light by exposing the material to much brighter light, to simulate the effect in 6 months of 10 years exposure. That's not necessarily the same thing, but at least I think it's a start to try to understand long-term damage. So the question then is, if you want to test if your lighting standards are good or not, and you increase the level by a factor of 10, and you measure it after 1 year, is that the same as 10 years at the original level? And this whole process of what we call the kinetics, the rate of change of some of these systems is actually, I think, the object of a lot of intense debate at the moment. But people are looking at it. I mean, I tried to mention that in my Prussian blue slide. People try to accelerate the damage process by looking at what happens when you increase the light levels to try to simulate the long-term possible damage at low light levels. I'm not sure the two are necessary. I have a feeling that actually life is a bit more complicated than that, but at least it's a start. I don't know if that answers your question.
Okay, thank you very much for the interesting presentation. My question is, do you have any special requirements to prepare object before investigation?
So it depends. Many of the objects I've described you can measure in situ. So in principle, many of the things I described for a painting, you can just bring the painting if you're allowed to transport it. In a few cases, so if you can extract a sample, then of course it means that the object is easier to handle. But I think provided that the object can be moved safely and is not too big, and you could ask him what is too big. Well, you can put something 1 meter by 1 meter in the beam, for example. If you want to put something the size of an elephant in the beam, then you'll have a problem. But I would say, an object the size of a refrigerator or something smaller, you could find a way to actually study it. That's a bad example because a refrigerator is thick and X-ray techniques don't penetrate very deeply. But certainly a 1 meter by 1 meter painting, yes, you could put that in the beam.
As I see that some experiments which you tell us about could be made on the laboratory equipment which are cheaper, and its laboratory equipment could be in universities, in the museum, in the Hermitage Museum, there is an excellent laboratory too. So the question is, how do you approve or disapprove the projects, scientific projects, for such precise equipment as a synchrotron?
Again, that's a very good question. So, almost all of our experiments go through an expert approval process. So, if you want to do an experiment, You submit a proposal twice a year, and I have panels of experts who look at the argument, the case, and say, is it a good experiment or not? And the best ones get time. On that particular case, I think they would ask two questions. Is it an interesting problem? And do you need a synchrotron to do it instead of a laboratory, a handheld device or a laboratory question? And my feeling is that if the measurements can be done in someone's laboratory, they would recommend that it should be done in the laboratory, that we would only use the synchrotron where you really need a synchrotron. So, for example, the spectroscopy I described, or where you need microfocus down to 1 micron and look at a very detailed, you can only, or phase contrast tomography, you can only do that with the synchrotron. The radiography of the scroll, the first scroll, that was done on a standard laboratory measurement. So I think the decision would be based on, is it interesting, and do you have to have a synchrotron? And if the answer is yes for both, then you would have a good chance to get access to the beam time.
So the second question is about the neutron, for example, neutronography, neutron tomography.
Yeah.
You're using the neutron tomography, the synchrotron is maybe the source of the neutrons, as I understand. It's the easiest, there is no laboratory equipment with the neutron sources, just on synchrotron.
This is true. Yeah. So if you want to do neutron tomography, you have to go to. No, I think you almost. I cannot think that it is possible to get small-scale neutron sources, but you can't do this kind of tomography. They're far too weak. You have to go to a central facility. Yes.
Thank you very much for your nice presentation and very popular explanation about so serious things. And very short question, what is your forecast about possibility of mobile devices? Because you know telephone and other devices are now mobile, and even X-ray is portable for museum and cultural heritage needs. When we are able to weight portable devices?
So I think it comes back a little to the previous question. There are small-scale portable devices which you can take into your museum, you can use it in the security of your museum, you can bring it right up to the object, and are often better. But there are things that you cannot do yet with a portable device. And it's difficult at the moment for me to imagine how you would get the brightness or the small spot or the sensitivity to small energy changes with a portable device. So as far as we can imagine into the future, maybe our imagination is lacking, but certainly for decades, I think that most of the work that I've described, most of it, not all, but most of it, you'd have to bring to a facility rather than using a mobile device. I mean, we could discuss at great length why some of the aspects of synchrotron radiation actually need a certain size. If nothing else, if you make our instruments much smaller, it means it's much more difficult to measure small areas and measure different energies more sensitively. So there's a physical reason why it would be very difficult, very challenging to miniaturize any of this to a form where it's portable. One more question, anyone? Yes, please.
Здравствуйте. Вопрос у меня такой. В своем докладе вы показали, как вы анализировали глаз мертвой пчелы. А могут ли в качестве объекта выступать живые объекты, ну, например, анализировать межклеточные обмены веществ или еще что-либо подобное?
So that's also a good question. So higher organisms we're not allowed to put in the beam. For all sorts of ethical reasons. But so that's a very interesting question. Could we image single cells? The answer is yes, we can, right? In fact, we have a beamline that will come on next year, where we will be able to look at the internal structure of a cell and, in principle, the living cell. The really interesting question is how long the cell can be studied in the beam without damaging it. Because if you want to understand a living cell, as opposed to a dying cell, then you have to measure it very quickly. So one of the challenges for us is to be able to make the measurement times very quick. But the reality at the moment is if we want to look at even a simple organism, X-ray beams will probably destroy the living, I mean, you'll still image it, but it will be a dead cell. But fast imaging techniques on cellular scale, yes, this is something that we should be able to do soon. Okay, so Michael Popov, colleague, or not colleague, strictly speaking, but I believe you want to make some closing remarks. Thank you very much.
Я не займу много времени. Спасибо огромное профессору Гаррисону за лекцию, за то, что он нашел время в своем плотном графике приехать и рассказать о том, что происходит. И я хотел бы сказать большое спасибо посольству Ее Величества в России, поскольку в эти сложные времена мы сегодня увидели, что наука и культура в эти сложные времена являются теми мостиками, которые объединяют, в общем-то, все нации и позволяют нам оставаться партнерами, оставаться друзьями, оставаться людьми, которые интересуются простыми, живыми, интересными вопросами. И сегодняшняя аудитория и вопросы сегодняшней аудитории показали, что действительно в России есть огромный интерес к тому, как сегодняшние достижения науки можно использовать в гуманитарном измерении. Профессор Гаррисон является бессменным членом созданного в Курчатовском институте Международного совета по научной политике. И я думаю, вот отвечая на, по-моему, первый вопрос, я думаю, что в ближайшее время на одном из наших заседаний мы действительно обсудим, какие сегодня предметы исторического наследия из российских музеев мы могли бы распределить между ведущими научными центрами, между Курчатовским институтом, между институтом Дейзи, между институтом Даймонд, для того, чтобы действительно посмотреть и проникнуть в те тайны, которые интересуют наших гуманитарных коллег. Это и археологи, это и антропологи, кто угодно. И еще раз хотел бы большое спасибо сказать за то, что действительно господин Гаррисон осветил ту деятельность научных центров, которая наконец-то открыта для ученых других дисциплин. Сегодня, слава богу, наши ведущие центры мировые научные открыты не только для военных, но и для медиков, биологов, как я уже сказал, археологов, искусствоведов и так далее. И очень приятно, что мы развиваемся в этом направлении. Поэтому я хотел бы обратить ваше внимание на то, что Курчатовский институт эту деятельность ведет, и наши коллеги подтверждают то, что мы идем в правильном направлении. В этом году был проведен большой семинар, который называется «Естественно-научные методы в гуманитарных дисциплинах». Материалы вот здесь разложены, вы можете все ими пользоваться. И я хотел бы пригласить всех, кто действительно интересуется, обратиться в наш институт, где мы совместно с нашими зарубежными коллегами, я надеюсь, можем помочь вам реализовать все ваши научные замыслы. Спасибо огромное вам, спасибо большое посольству, спасибо организаторам, спасибо за то, что пригласили. Ну и помните, что в Российской Федерации есть возможности комплементарные и нейтронные, и синхротронные возможности для изучения нашего культурного наследия. Спасибо большое. Спасибо. Я хотел бы обратить внимание, что профессор Гаррисон сам является примером комплементарности, поскольку до того, как он возглавил Даймонд, синхротронный он возглавлял нейтронный центр Института Лаве-Ланжевена во Франции. Спасибо.
That's the end of this afternoon's wonderful lecture. Thank you all for your active engagement. Do come and talk to my team here from Moscow, St. Petersburg. If there's anything you want to do, keep in touch, follow up, have some new ideas. But again, thank you, Professor Harrison. Thank you most of all to Professor Petrovsky and the great team at the Hermitage. Thank you all very much.
Спасибо большое. И последнее напоминание. Не забудьте, пожалуйста, сдать наушники перед выходом. Спасибо.